Yeah, thanks, Alex, and good afternoon, everyone. Yeah, apologies for those of you who have come for Sylvan's talk, but you'll be relieved to know that we've got some pre-lunch experimental decay just to improve your appetite for the buffet. Experimental taphonomy is by no means a new field, and there's been numerous studies over recent decades, perhaps most notably by Derek Briggs and his colleagues. I'm just using these three examples to summarise the field, because I think we can split them into three broad different types. So there's those studies that are looking at gross morphological change, those studies that use some sort of measure of the total amount of loss of information, and those that make some attempts to replicate the process of preservation. But more recently, there's been a slightly different approach which focuses on the transformation and subsequent loss of individual characters. So the first paper really was this by Robert Sansu and colleagues. Now the real power of this kind of approach is that we're able to answer fundamentally different questions. So including, for example, assessing the relationship between decay and bias in phylogenetic reconstructions. And also, shameless plug, this paper came out earlier this week. We're able to examine the suites of different characteristics and how they relate to actually interpreting the fossil record, and transformation of individual characters. For example, the outer cuticle here of this onychophron in comparison with this apparent double wall body line of this Xinjiang lower podium. But there's a fundamental problem with decay experiments, and that is that there is a long way between the conditions that we rot things in the laboratory and the conditions that animals would have rotted in their original deposition environment. So how can we go about trying to understand the effects of these environmental conditions? Well, one approach would be to take our bucket and our animal of choice, in this case it's an Amphioxus, and make some assumptions about the environment and prescribe the conditions that we think that the animal will have originally decayed in. Now, this is unsatisfactory for a number of reasons. Firstly, because we can't actually get at those original environmental conditions very accurately, but also we would have no idea as to how they're actually affecting the results of decay. So an alternative approach would be to take some list of environmental conditions and run experiments with every possible combination. So if, for example, the presence or absence of oxygen and temperature. But we know that two variables doesn't adequately describe a deposition environment, so we'd have to go about progressively adding different variables, say, for example, sediment type. And the more variables that we add in, we increase the number of experiments that we have to run alarmingly, in fact exponentially, is described by this little formula here, to the point where if we want to make any attempt to accurately describe a complete deficit environment, we'd have to run more experiments than one person or indeed an army of undergraduates could achieve. So the approach that we've taken at Leicester is to, first of all, establish a null model, so that's making the fewest number of assumptions about the environment that the animal is decaying in, and then add a single variable and directly compare the rate and sequence of decay or loss of characters between those two conditions, and then repeat this process with another variable and progressively build up a more sophisticated model of how we understand how environment interacts with decay. And so how do we go about actually collecting the data? Well, we come up with a list of informative characters based on whatever the question that we're trying to answer, and a regime that we're going to sample those the specimens. And at each of these sampling intervals, we destructively sample 3 individuals and assess the state of each of these characters by whatever metric you want to use. And then it's just a simple case of counting the number of specimens, the number of individual samples for each interval where we still see that character. So it's just a total of the number of yellow and orange for each of these characters. And from that data we get a proportion of character retention throughout the whole experiment, and we can simply rank that character retention from the most decay prone down to the most decay resistant. We can also then plot up those character retention values, so that's the proportion of samples that retain that character throughout the experiment between our null model and the treatments that we're trying to address. So just to key you in as to what's going on with these plots, because they're a little bit complicated. So our most decay-prone characters plot down here in this area of the graph. So in Amphioxus, that's things like the eyes and the atrial core. And our most decay-resistant characters plot up here, things like the notochord and the myomeres. So where these points plot in this field is informative about the nature of the retention of those characters. So if points plot on this one-to-one line, then there's no significant difference between character retention in the null and in the treatment. But if they plot up here in this field, then we've got an enhanced character retention in our treatment. So just to give you an example, so a character that is retained in half of the samples in the standard might be retained something like 75 or 3/4 of the samples in our treatment. Conversely, if points plot down in this field, we get the loss of characters is enhanced in the treatment compared with the null. So again, if we took that 50% character, it's retained in less than 10% of the samples in our treatment. But we can also plot a regression line through that cloud of points, which we've done here, and the slope of that line is informative about the rate that decay is taking place. So if here we have a slope that doesn't differ significantly from 1, so in other words parallel to this one-to-one line, then we have no significant difference in the rate of decay. But if we have a line where the displacement between your regression line and the one-to-one slope is greater in your most decay-resistant characters, then we have a faster rate of decay. And conversely, if we have the biggest displacement in your most decay-prone characters, then you've got a slower rate of decay. Okay, so don't worry if you've not followed me exactly with everything I've gone through. These little cartoons are going to be next to all of the plots, just to keep you in what I'm trying to get across. So we've been conducting experiments on 2 different animals. We've got the cephalochordate Amphioxus and this polychaete annelid Elytta or Nereus, depending on how old the literature is that you read. And we've conducted these experiments with a range of different variables, some for both, some for just one of these organisms. So I'm going to try and whiz through the results of these experiments. So first of all, animal size and the presence or absence of a microbial inoculum makes no difference to rate or sequence, so I'm not going to talk about those anymore. But temperature, as you might expect, does make some difference. First of all, though, if we compare the sequence of decay, if we look at a Spearman's rank of the ranks of decay resistance, we see no significant difference between the hot and the cold treatment. If we plot up the character retention data, as you might expect, we have both enhanced character retention and a slower rate of decay in the cooler setup, which isn't surprising because everybody knows that refrigerators work. So that's just to give you an idea of how we can interpret these results. Perhaps a more interesting result is we looked at the relative volume of liquid around the animal in this experimental vessel. So we had same size Amphioxus in 2 different vessels, this little cuvette and then this relatively big box. So again, there's no significant difference in the sequence of character decay, but if we look at the rates, so this is the one-to-one line, this is our standard, this is our animal which has lots of fluid, and there's no difference between the slope or the intercept of these lines. But when you restrict the amount of fluid in which the animal is decaying, then we do see significant difference in both of these. So we're getting a slower rate of decay and retention of characters. And in fact, as the experiments progress, we actually see that we're getting a faster rate of decay later on. So we've got initial character retention, and then once things start to rot, they're going quicker than they were in the standard. Okay, but perhaps more interestingly, we've been looking at the effect of different substrate. So we've been sticking our critter in muds of various different kinds and some artificial seawater. And this is some a summary of data for the polychaetes. So the thing I wanted to take away from this slide is that we have no significant difference in the sequence of character decay in any of these treatments. But there is definitely some interesting things going on in terms of rate, which is borne out here if we just compare the whole worm in bentonite or montmorillonite and in kaolinite at day 12. So we've basically just got a snotty sludge in the bentonite, but we've got this beautiful worm with most of its anatomy preserved in the kaolinite. Again, if we look at the anterior anatomy at day 24 in water and in mica, we get jaws and aciculae and then a rough body outline. But in kaolinite, we still have lots of features of the head and the parapodia, and in bentonite, all we have is the jaws and the aciculae, not even an outline of the body left. This pattern is borne out if we look at the character retention data, so no significant difference between mica and water. In kaolinite, we see the slope of the line doesn't significantly differ from 1, so we don't actually have a difference in the rate of decay, but what we are seeing is that an enhancement in the retention of character. So we have an initial period of almost no loss, and then decay proceeds at the rate you might expect. Conversely, in bentonite, we see no difference in the intercept of this line, but a highly significant difference in the slope. So we have a much faster rate of decay in bentonite. We also have some preliminary results for Amphioxus. So these experiments have only just finished and haven't had time to crunch all of the numbers. But you can see, hopefully, that at day 4, we have this beautiful Amphioxus preserved in kaolinite with almost no loss of information. And again, in bentonite, we have this sort of snotty sludge. But by day 42 of these experiments, the kaolinite is actually caught up with the bentonites. It's hard to tell what this animal is in either of these cases. So again, these numbers are preliminary, but it's worth having a look at these character retention plots, because we do see the same or a similar pattern in kaolinite for the Amphioxus as we saw in the ragworms, in that we have a significant difference here in the intercept. So we are seeing character retention, but it looks like that we don't actually have a significance at a 5% significance threshold, but at a 10% threshold you do see a significant difference in the slope, which indicates the same pattern that we saw in those restricted volume samples, where you have an initial period of no decay and then actually a more rapid period of decay afterwards. So perhaps that's what's going on. And again, we don't see any significant difference in the bentonite, but I think this is because we just don't have enough data to actually go into these plots to pull out significant results, but we'll have to sort of wait and see. So just to briefly summarise these results, so one of the main take-home messages is that we never see any difference in sequence, no matter what we do with these experiments. We do sometimes see effects of rate, changes in rate, in terms of temperature, which is what you might expect, but also this more interesting result in terms of the amount of available liquid in which the animals decay. And again, in our substrate experiments with mica, we don't see any difference between mica and water. We don't see any difference in sequence with any of these treatments, but we do see this difference between kaolinite, a general increase in decay in kaolinite, a general decrease in decay in the kaolinite, and a faster rate of decay in the bentonite. And exactly what is going on, we're still teasing apart, but what I think is going on in the kaolinite is you've got this protracted period of no loss, and then once decay starts, it actually proceeds much quicker than you might expect. But you're probably all sitting there thinking, well, why should I care about any of these results for these experiments? Well, there's two things that I want to take away. One is that sequence is really important. So if we're going to make comparisons between biases from decay and biases based on phylogeny, then we need to know that sequence is robust to the conditions in which these animals were decaying, and we've demonstrated that is the case. So it doesn't matter which environment you're rotting your animal in, the sequence is always going to be the same. But rate of decay is still really, really important. And actually it's most important when we want to think about how we go from the processes of decay to the processes of preservation, so how we go from a rotten animal into the fossil itself, in terms of windows that we can preserve different kinds of characteristics. So we're looking more and more into the relationship between rates. So I've just got a few people to thank, not least Rob Sanson and Theo Beecroft, who actually collected some of the data that we've analysed, and of course the two critters that laid down their lives for science. So, and of course to you as well, thanks very much.